Yeah, because over the next couple of weeks, I'm also out of town the week of the 20th, so there's like these gaps. And the 27th, I come back, that's a Wednesday, so or whatever. The class preceding that, we have a class before that, so we can sort of go over the material we've covered so far. And I didn't want to give the midterm. I come back, we have one more class of lecture where we basically have to review stuff, and we really haven't done that much. I'm not going to quiz you on pure probability, so all we've really done is correcting codes so far. All right. Nobody seems to be jumping for joy, despite 3 pieces of good news. Yeah? All right. Okay. Any questions on Hamming codes, linear codes, check matrix? The homework's been graded, the first one, and should be, hopefully the grade will be coming by at the end of the class, and it'll be distributed. Otherwise, next week. Yeah?
Why does the check matrix have to be in that particular form?
Why does the check matrix have to be in that particular form? It doesn't have to be in that particular form, but for it to have the properties that it has. So you could permute the various columns. Can you do that? Permuting the various columns permutes how you compute the check bits. So that form corresponds to the code that we set up, right? I mean, the top row corresponded to how we computed the first code bit, and the second row corresponded to how we computed the second row bit. So you're really just reapplying those equations by multiplying the matrix with the received code word. So that's why it has to be in that order. You could permute the rows, definitely. Permuting the columns changes the code. Okay? Yeah.
I remember you saying, maybe I heard it wrong, that it doesn't have to actually be a valid code word. That it only has to. You make it like the C is 100, and as long as the C1 is correct, or
if it's a valid code, well, I'm not sure. The check matrix. The check matrix. You take the check matrix and you multiply it by some received code word. Okay, you'll get 000 if this is a valid code word. It doesn't have to be the one that was sent, right? But if enough bits permute, if enough bits flip such that you wind up with another valid code word, or in this case, a valid code word is defined as a valid code word is a 7-bit sequence. So we have B1, B2, B3, B4, C1, C2, C3 that satisfies B1 XOR B2 XOR B4 equals C1, right? That was the code. So any valid code word satisfies this property. So if you send a code word that's valid and bits flip and you get enough bits flip, you might wind up with another valid code word, right? So for any valid code word, you're going to get 000. For any invalid code word, you're going to get something else. And that something else tells you which column you want to flip, which bit you want to flip in order to convert your invalid code word into a valid code word. And every invalid code word is distance 1, Hamming distance 1 from a valid code word in this particular code, turns out.
I was actually asking about each row of the check matrix.
Each row of the check matrix checks. So for instance, the top row confirms whether or not this property is satisfied in the received code word.
So it doesn't matter about C2 and C3?
Not in the top row. The top row only checks the C1. The second row checks the equation for C2, and the third row checks the equation for C3. Yeah, Sebastian.
If you end up with a check matrix that's not like, it doesn't have unique columns, or has 000 as one of the columns, what does it mean that you can, in every case, you can't go back and correct the error, or
If 0, 0, 0 is one of the columns.
You know, you have like the same columns for like B, B2, and C1.
Well, so if you have 0, 0, 0 for a column, there's some bit that corresponds to that column. If you flip that bit, it's not going to affect the syndrome, which basically tells me that that bit doesn't even appear in any of the equations. That's what 0, 0, 0 means for that column. If you have two columns that are similar, then yeah, when one bit flips, so suppose the syndrome you get matches the column that appears multiple times. Well, then you don't know which bit to flip. Okay, just drop it off. That's the homework. Homework number 1. Thanks, Michael. And just pass it around. If you have two columns with the same values, and yeah, you don't know if you're told one bit flipped, you don't know if it's which bit it corresponded to. So you can detect it, but you can't correct it. You're not sure which one. Okay? Any other questions? Excuse me. Okay, so we're going to consider cyclic redundancy checks today, which is another form of error correcting code, and this is actually used in the internet. To detect. We generally don't correct. Flip bits. Okay? And the idea is really simple. So let me first explain the idea to you so the actual computation is done in what's called Galois field to the n. There's some weird algebra, exclusive OR algebra, but I don't want to get too into that. I'll show you how to do it in Galois field 2 to the n. It's easier for a computer. It's easier for a computer, but harder, a little bit harder for intuition. Okay, so for easy intuition, what we're going to do is do it in our normal real. Actually, in the integers. So CRCs. In the integer plane, z plus. Okay, so here's how it's done. A message is a sequence of bits. It's just a number, right? I mean, any sequence of bits you can assign treat it as a binary representation for a number and give it a value, right? Right, so for instance, 101101 is 1 plus 4 plus 8 plus 32. 1 plus 4 plus 8 plus 32. 13, that's 45. Right? Okay. And here's how we're going to do our error check. Choose what we call a generator. G, which is a number smaller than the typical message. Much smaller typical message. Okay? So, for instance, if the message is 128 bits, G is like 8 bits. Okay, so the message is some number between 0 and 2 to the 128 minus 1. G is a number between 0 and 255. Okay? divide message M by G, okay, and let R be the remainder of M divided by G. Okay, so for instance, if M is 45 and G is 8, then R is going to be the remainder of 45 divided by 8, which is 5. Okay? Everybody with me? Okay, and then you send the pair M comma R. Okay? And I should have mentioned that receiver and sender agree on number of bits in M and value of G as part of protocol. Okay, so I should have said that over here, right? I mean, before we started talking about the process of how you actually, what the computation the sender does, the sender and receiver agree on the number of bits that are going to be in M and the value of G. Okay, and then the sender, with this agreed upon G, takes its message M that has the agreed upon number of bits and divides M by G, computes the remainder, sends the pair MR. Okay? Receiver receives M prime R prime. Okay, some of the bits may have flipped. Computes. Let's see, how do I want to do this? Let's do M prime minus R prime divided by G. Okay. And if does not equal 0, reports error. Okay? I mean, think about it. If you have M and you subtract off the remainder before doing the division, then you should be able to divide that quantity evenly, right? I mean, this step, that's the same as M prime divided by G not equal to R prime, and you say error. People see that? Right, I mean, like 45 divided by 8 gives you a remainder of 5. 45 minus 5 divided by 8 is going to be 0. So, okay. So in a nutshell, that's how you do a cyclic redundancy check. I mean, it's not very hard. Yeah, Ron.
On 8, you said divided 45 minus 5 divided by 8?
Yeah.
Equals 0?
Yeah, 40 divided by 8 is 5. Right? 40 minus 5. Do the minus first, then divide by 8. Okay, what's the efficiency of this code? You look puzzled, some people. Why? Any questions?
40 divided by 8 is 5 times 0 is 8.
Oh! Sorry. Yeah. Yeah, thank you. If the remainder does not equal 0 of this computation, if it doesn't divide evenly, sorry, my bad, then report the error. So it's the same as that. Okay, so what's the efficiency of the code? Yeah. Well, it's close. There's a number of bits in M. Plus number of bits, not in R. Oh yeah, in R. Number of bits in R. Well, number of bits in M divided by that quantity. Right? Every time we want to send an M-bit message, we have to send those M bits plus these bits in R. Okay? A number of bits in R is less than or equal to the number of bits in G. Right? I mean, because the remainder can't be bigger than this generator, the thing you're dividing by. Right? So for instance, what I said over here is if your message M is a 128-bit quantity, and G has 8 bits, your efficiency is 128 divided by 128 plus 8. Right? So it's very close to 1. It's a very efficient code. Okay? What's the probability it fails to detect an error? Okay, I'm just looking for an intuitive proof because actually proving this result is not that easy. On average, what's the probability that if there's some bit errors, what's the probability that they don't get detected? But what happens when you get bit errors? Huh? We're not flipping bits in G. We're flipping bits in the transmitted M or R, right? So instead of getting M and R, we'll get M prime and R prime. So there's some bit errors. So what's going to happen?
Well, in order to not detect an error, there has to be G bit flips, right?
You're kind of on the right track. The point is, there'd have to be enough bit flips. There'd have to be the right set of bit flips, such that the change, when you divided M prime by R prime, you still got a remainder of 0, right? And there are G possible outcomes for the remainder. Okay, so there are G possible remainder values. Sorry, and this was EG. Right? So if you imagine if you flip bits at random, you're going to wind up with a random remainder when you do the computation. Right? If arbitrary bits are flipped, The value of the remainder in the receiver's computation is arbitrary, right? I mean, this is just a sketchy proof. It's just using your intuition, right? I flip a couple of bits instead of getting 0. If my G had the value of what I say, 8. If my G had the value of 8, I might wind up with 0 through 7 as a remainder. So just think, suppose they're all equally likely, right? The value of the remainder is arbitrary. So G minus 1 out of G times the error will be caught. Right? Because I flip a bunch of bits, any value of the remainder other than 0, I'll catch as an error. Right? If the value comes up as 0, well then that's the one time it happened to get away. So the failure rate is 1 over G. Roughly. I mean, it's not exact. I mean, it really depends on how you flip the bits and how it changes the message and yada yada. Whether you pick a good value of G, which we're not going to worry about those details. Okay, but the idea is this is why this code it's liked in practice. There's very, very good efficiency. Okay, with 8 bits, this is a very, very small quantity, right? 128 is what? How many times 8? 8, 16. 16, right? So this is the efficiency 16 over 17, right? So for every 16 bits of data you want to send, you have to send 1 additional bit of error correction. Okay? And the likelihood of an error is 1 out of 55. It's pretty good. And if you wanted, you could double this, double the length of G. Your efficiency would drop a little bit. And the likelihood of an error would be 1 over 2 to the 16, which is like 1 out of 65,000. Okay, it's the value of G, not the number of bits in G here. Right? So here, the efficiency is a function of the number of bits, grows logarithmically with the value of G, and the failure rate is linearly inverse to G. Okay? And the only difference is in the computer world, this is done in Galois field 2 to the n. So I'm going to do, it's the same process, just done in this other field. So here's what you do. You have this message to send. So this is now how a computer does it. Okay, you have this message to send M. Okay. Let me do it this way. Let's say a message to send capital M, which has M bits in it. Now let's do it the other way, just to be consistent, even though I'd rather use big M for the message. Message to send M with M bits in the message. Okay, we have a generator G. With, let's say with n bits. Okay, so the remainder is going to have at most n bits. Okay, and now here's what's done. Compute 2 to the n times m, which is basically padding, I guess, 2 to the 0. Yeah. You're padding n bits onto the end of m when you do this. Okay. Plus 2 to the n times m. It's a remainder of 2 to the n times m divided by g. So you're taking this quantity. Okay, so I should do an example. Let's have M be 0, 1, 1, 0, 1, 0, 1, 0. Let's have G be something small. 1, 0, 1. Okay? So 2 to the n times m is just going to be 0, 1, 1, 0, 1, 0, 1, 0. And then to multiply by 8 in this case, you just pad on 3 extra zeros. Okay? And now we have to divide 2 to the n times m by g. Okay, where this division is Galois field 2 to the, well, in this case it's, 2 to the n. Okay, and I don't care that you know how to do this. To check you know how to do the division Galois field 2 to the n. I'll just do it to show you, but I care more about that you understand how the cyclic redundancy check works. So I care, all you have to know about it is how it works in the real space, or in the integer space. All right, just so you get a sense. So this is how a computer does it. So you take this 2 to the n times m and you divide it by g. So it's 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, divided by 1, 0, 1. Okay? And this division in this case is a lot like regular division, except it's all done with XOR. Okay, so it's sort of weird. But since I'm not going to quiz you on it, I don't care too much if you really understand this or not. So pay attention as much as you want. But basically what you do is you check to see whether this quantity fits into the current, like you normally do division, right? Does this divide into this? No. If it doesn't divide into it, you put a 0. Okay, and you carry the value down. And you bring down, you sort of go on to the next round. And now the question is, actually really the question is the first bit a 1? If the first bit is a 1, okay, when you XOR these two quantities together, the quantity reduces, and then you put a 1 up here. So put a 1 up here, and I bring down the 1, 0, 1, and then instead of addition subtraction, I take the XOR, so I'll wind up with 0, 1, 1, and then I bring down the 1, and I keep repeating that process. So again, 1, 1, 1, yeah, that's got to be XORed. 1, 0, 1 comes out to 0, 1, 0. There's not a 1 here, so I don't do the division. Now I bring down the next quantity, 1, 0, 1. It divides in evenly, etc. Okay. Anyway, this is how I'm going to compute my g. Sorry, this is how I'm going to compute. This is how I'm going to do the division. At some point, I'll finish and I'll have a remainder. Okay, there'll be some quantity down here. I take that 3-bit remainder and I add it to this, which just means it replaces these last 3 0 bits. And that's what I send to the receiver. Okay. And then just to finish up, the receiver takes received quantity, divides by g, and if remainder is non-zero, then error. Otherwise, truncate last n bits off message and deliver. Okay? So the point is this quantity, when I add on the remainder to this quantity over here, I'm doing the same thing as I am over here. Where did I do it? Basically I'm doing this. I'm doing m prime minus r prime, or m prime plus r prime. It doesn't make a difference when you're in Galois field. Minus and plus are both XOR. Okay? So the quantity that I wind up sending should be divisible by g. So if I divide by g, I should get 0. If I do, I can just truncate these last n bits, which were the remainder, right? I just shifted over the message. So this part in Galois field 2 to the n is just for your interest in case you ever really want to write cyclic redundancy checks. Okay, and then there are good values for G and bad values for G. If you have any more questions on it, I'll be happy to talk about it in office hours. But I'm not going to quiz you on the Galois field 2 to the n part. Okay? Any questions on that? Yeah, Ron.
Why do they call it cyclic redundancy?
That's a good question.
Why is it? Well, you know why it's a check, right? Why is it cyclic redundancy? Well, these are cyclic codes. And why is it a cyclic code? I don't know. It's a good question. There's probably an easy explanation. I just don't remember it. But you know, the codes I showed before, those are linear codes. Why are these cyclic? Maybe division is in some sense cyclic, whereas addition is linear. I don't know. And I should also say, choosing good values of G goes way beyond what we're doing in this class. So traditionally in these, when you're transmitting bits, right, the arrows actually tend to come in bursts. So you actually want, the way we've been looking at Hamming codes, it doesn't matter if the two, or Hamming distance, doesn't matter how far apart the two bits are that get flipped, right? But in reality, you're more concerned with bits near one another being flipped because that's more likely to happen. So you want to design these codes such that they're more likely to pick up on bits close to one another being flipped. So they talk about the efficiency of these, or the ability to correct, you know, certain length strings of bit flips. You know, if 5 bits get flipped in a row, this will always detect it, that kind of thing. Or I guess the other way around. If there is no sequence of more than 5 bits getting flipped in a row, it'll always detect it, something like that. Anyway, I just want you to get the basic idea. This is another way to do a check. Okay? Any questions? Any other questions? So I'll just leave you with a thought. There's a really hard field called coding theory. It's a really hard field. Okay? And the field is all about asking the question, what are good codes? So codes are not something that's really well understood. I mean, we know good codes. There are some codes that are good, and there are some that are not good, and they have ways of finding some good codes. But there's no, I don't know, have you ever, it's like number theory. I don't know if you've ever taken a course in number theory. But numbers just are, facts about numbers is just really weird. You know, it's like prime numbers. Well, how do you decide whether or not a number is prime? The only way people really know how to do it is to try and factor it. Like, there's no like magic test you can run. Like, if you want to know if a number is divisible by 2, all you got to do is look at the last digit. If you want to know if a number is divisible by 3, you just add all the digits together, and keep adding them together until you're left with one digit. Keep repeating that process. And if that's divisible, if that's a multiple of 3, 3, 6, 9, then it's divisible by 3. But there are lots of things that have known tricks like that, or that we know of. And so coding theory is a really hard field, like number theory, in the terms that it's hard to predict what's going to happen. So if this kind of stuff excites you, consider a hard but interesting career in coding theory. And I do coding theory, so it's not like I'm plugging my own field. Okay? All right, so we're going to move on. We're going to move off of coding theory, error correcting codes, or detecting codes now onto the next subject, which is still in the data link layer. dealing with collision resolution. Or what's commonly referred to as multi-access collision resolution. And this is usually just truncated as MAC. Okay, so like MAC ID, that's this MAC. If you ever heard that term? The ID was originally constructed because you had to deal with multiple devices that might collide and you need separate identifiers for them. Okay, so what's the problem here? You've got, I guess it's most interesting, we got 3 devices, okay, and I guess these days it's easy to think about it in terms of a wireless medium, right? So suppose A and B both want to communicate a message to C, okay? If they transmit at the same time, then, if A sends its message and B sends its message, then, you get all this noise at C. They interfere with one another. Like, if your mom and dad ever yelled at you at the same time, you're getting yelled at, but you're not really picking up the information that they necessarily want to get to you, right? It's the same thing here, one at a time. So this is all about how you get 2 devices to transmit one at a time. And the naive approach would be if A and B fail to get their message through, then try again, right? But there's always this concern that especially with computers that are much more synchronized than humans, they'll keep trying to transmit and they'll just keep colliding over and over and over again. Okay, so people came up with methods to help reduce the likelihood that the collisions will collide. Okay, so how to reduce the likelihood that your message collides with other senders. Okay, well, let's first set up a model of our environment. A little bit more formal than my picture up there, but not much. Okay, so suppose it takes time, use capital T, to transmit the message, to actually get the bits out, actually spit out the bits. Right, the bits aren't sent in parallel, sent in sequence. There's a certain amount of time that it actually takes just to even get the bits out onto the wire or into the wireless environment or what have you. Right, so we'll say it takes time t to transmit the message for all transmitting devices. And suppose it takes time tau so another time for a transmitted bit to reach intended recipients. Okay, from all send devices. Okay, so somehow, I mean, this is it's very unlikely that every device is going to be positioned such that it takes exactly tau, but for the simplicity of our model, we'll assume that. So this is assumption number 1. Assumption number 2. Assumption number 3 is suppose if there is any overlap in transmission, let me just make sure I do this right. Okay, let's say anywhere. Is that right? Let's get rid of anywhere for a minute now. At the receiver. Then all overlapping messages are corrupted. And corruptions are detectable, are always detectable, never correctable. Okay, so if we have this overlap and some bits get messed up and we're using something like a cyclic redundancy check, so we can detect that there's messed up bits, but we can't correct them in the message. So let me draw a timeline of two senders and a receiver. Okay, so here's sender 1. Here's the receiver. Here's sender 2. And the x-axis is time. Okay, so time going this way. Okay, so at some point in time, sender 1 wants to send a message to the receiver. So let's say it starts here. Start sending message at this point in time, and then a time t later. Right, so this distance is capital T. It completes sending that message. Right? That's what we said. It takes time t to send the message. Okay? And then that message actually gets the receiver sometime tau later. So this distance here is this propagation delay tau. Okay? So the message arrives there, and during this interval in time of length t, right, sender 1's message arrives. Okay? And it's also going to arrive at sender 2 here. So at the same point in time. Okay?
Why sender 2 gets sender 1?
I mean, everybody's receiving, I mean, you can't distinguish. It's just everybody, you know, especially these days in wire environments, you can imagine it. Used to be, even when you had stuff connected by wires, it was a broadcast medium. So you can't control who gets it. Okay? Okay? And maybe sender 2 chooses to start transmitting here. Okay, so again, everybody's message is of length time t. So sender 2 sends a message, and sometime tau later, it arrives at the receiver. Okay, so again, this distance here is also tau. Okay, the time from when sender 2 starts transmitting to the time when it arrives at the receiver. And of course, also at the other sender. Oops. Right? Yeah. Yeah. Length t. Okay? Everybody follow the picture? Yeah, Patrick.
Are you saying that the total time between sending and receiving, not on just with one message, is 2t plus tau?
Sorry,
The total time for a message to be sent and received is 2t plus tau, or just for the sender to send, the time to travel, and then the time to receive?
Let's look at that next. We're going to try and figure that out. But right now, I'm just trying to demonstrate pictorially what's going on. Basically, when you send something, it gets to the receiver time tau later. So let's see. Well, let's not go there yet. So given this, and so there's a collision here. So the information, both senders' information is lost. Okay. So now we're going to look at several different collision resolution protocols that have been proposed. So first one, the simplest. Well, actually, let's first look at what you can do. Okay, you can just send blindly, hope it gets there. Okay. Okay, so here I think is what Patrick's question is. Suppose you're a sender, and you send a message at some time t, right? Okay. Let's do this. Let's do this following the rules that I said. So this is your message of size t. Okay, and tau has some value. Tau is the propagation delay. So and you get a message from another sender at the same time that a receiver would, right? So your message is gonna. So let's say this distance is tau. Let's have tau be this small distance. Then the receiver's line must be clear So let's say you start, let's call this time t, the time at which you start transmitting. Okay. So t is the time the sender starts transmitting. Then receiver's line must be clear of other transmissions during the period t plus tau to t plus tau plus t, right? This is when my transmission will first start arriving at the receiver, and this is when my transmission will complete arrive at the receiver. So no other transmissions come in that time. Okay? Excuse me. So let's, and what can I do? I can check my own wire, or I check my own, a sender, let's say this, can, or let's say might, be able to sense its own line. Okay, so to see if transmission is currently, a transmission is happening right now from another device is happening. It's transpiring. So I might be able to detect, can be used to detect collision. Or delay my own transmission. Or delay own transmission. Okay, so right, I'm some device. I may have sent out a packet, and then I can sit there and listen to the line. And if I wind up getting somebody else's packet before this additional time of tau has elapsed, then I'll know, hey, there was a collision at the receiver. My message didn't get through. And I can also do this before I decide to send my message. I can sense the line, and if it's in use, I can say, all right, I'll wait. I'll wait till this other guy finishes up before I transmit. Okay? Everybody follow the different versions? Yeah, Sebastian.
So the message to all the devices and
Yeah, it's sent everywhere. Yeah. So it's like a room full of people. Once you start talking, everybody's going to hear you. So imagine talking where in a big stadium where we all have bullhorns, and there's this long delay before your transmission reaches the other end. So there's a possibility that it increases the likelihood two people will start talking at the same time. And if someone's already talking on the, so you could be talking, everything could be quiet. You could start talking on the bullhorn, and you'll stop. And, so imagine everybody speaks for the same amount of time. If you hear somebody else talking as soon as you stop, then they obviously started talking while you were talking, and whatever you were saying get through to everybody in the stadium. And likewise, if you hear somebody else talking, you can decide not to start talking, right? It wouldn't be very prudent. It's very unlikely, given that your message is probably longer than propagation delay. If you started talking while they were talking, there's a good likelihood that your talking is going to collide, and neither person's message will get through. Who's getting what I'm talking about? Because, boy, you can never tell from the way people look at you. Students always like. In fact, I remember one time when I gave a talk at a conference, and there was one guy sitting in the front who was going like, yeah. So I knew I was at least getting through to one person. So it was, very motivating to have me keep going. It's a real confidence booster. When students give talks at conferences, you should always have someone in the front row going, Right. And hopefully you get it, right? They're not just acting. All right. So let's start looking at some different versions of protocols. So the first version came out, and it came out from the guy's name was Abrams or Abramson. Had a really rough life because he was working in Hawaii. So he came up with the Aloha protocol. Okay, this is the first collision resolution protocol. Came out in the 70s. Okay, not surprisingly, designed by a guy in Hawaii. Okay, who in Hawaii, right? It's a bunch of islands. They were just starting to build communication networks, and you know, they had to send messages from island to island, and so it was easier to do it using wireless technology. But you had this collision problem. Okay, so it's a very simple protocol. Choose a lambda. Okay. Wait a random amount of time. Before sending a packet. This is the time. Wait a random amount of time before sending the packet. Parentheses, that is exponentially distributed with rate lambda. See, the stuff actually gets used. Okay, then send. So the whole point was to put in this randomness. So if you didn't have the randomness and you tried to send your packet and you got a collision, boom. You have to wait some time, maybe 0, before you send it again. But if two devices are colliding, they keep trying to resend right away, they'll just keep colliding. So the idea is you have somebody's got to back off, right? Somebody's got to wait and let the other one go first. But you want to be fair to both devices. You don't want to have one device always back off, you know, giving it more priority than the other one. So the idea is both devices just pick a random time, they both back off, and hopefully one will go before the other. Okay? Actually, there were two properties I forgot to mention in our probability review. But one of them is just if t is exponentially distributed. So this is an aside for a second. T is exponentially distributed with rate lambda. What is E of t? So t is an exponentially distributed random variable with rate lambda. What's the expected value of t? Anybody know? 1 over lambda. Yeah. Anybody got to compute that real quick, based on what I did give you? Right? We said for a continuous random variable, E of t is the integral from 0 to infinity with the probability that t is greater than t. Remember that? Right? So that's just the integral of 0 to t of e to the minus lambda t dt, 0 to infinity, sorry. Right? So you're going to integrate this, you're going to get minus e to the minus lambda t over lambda. Zero to infinity. And when you plug in infinity, you get 0. When you plug in 0, you get 1 over lambda. Or minus 1 over lambda. Yeah.
Isn't it the density that you're integrating?
You would integrate the density of t equals t times the density of t equals t. And we showed that that's equivalent to this. Look back in your notes. The two turn out to be equivalent. And you know, you write it as a double integral. You reverse the order in which you compute the integrals, and you can just solve it that way. But if you did it using the density function, you get the same thing, where it would be t times the density, since we're computing the expected value. Okay, and the other fact is something called PASTA, which stands for Poisson arrivals C time average. Okay, and in a nutshell, what this is saying is, for our purposes, if a system reaches steady state, right, which is those pi sub i's are the Markov model probabilities in steady states. Then after waiting a time, that is exponentially distributed, the observation of the system corresponds to the steady state probabilities. So think of it this way: if you have some Markov chain, and the Markov chain has reached steady state, then whenever you wait, I mean, in some sense what I'm saying sounds redundant, but you wait a time that's exponentially distributed, and then you look at the Markov chain, and the probability of being in a certain state equals the steady state distribution. And again, if you wait a time that's exponentially distributed, that'll always be the case. Okay. I'm just going to apply that result. You probably won't even notice that I'm applying it because it follows your intuition. But I'm not going to test you on that. But we're going to use it. So I just wanted to if anybody ever does catch me, like, how can you make this assumption? If I say pasta, you can't say I didn't show you what I was talking about. So. Okay, so what is the performance of Aloha? So suppose you have n plus 1 devices in total. Okay, so if I'm a device transmitting, then it's my device and n others. So we just use n plus 1 because assuming I transmitted, what's the probability I collide with these n other devices? So we'll just be able to use n instead of n plus 1. Okay? So let's do this. Let's do this. Okay. Okay. Try to think about how to this formula with random variables. Yeah. Okay. Let S sub I be the time of device zeros ith transmission. Start. Okay, so SI will be that time. Okay, and let XI equal 1 if transmission is successful and 0 otherwise. Okay? If ith transmission of device 0. If it's successful, 0 otherwise. If ith transmission of device 0. Okay? And what we want to compute is the probability that xi equals 1, the transmission is successful, given I'm not crazy about this notation. Given SI equals T, sometime T. Okay? So what am I saying is happening? Right? Here's some time T. My device is transmitting. I'm going to be transmitting for this time capital T. And then I also need this additional time tau for my transmission to propagate to the other devices and to the other receiver. And no other device can transmit when in order for my transmission to be successful. Huh?
Between T plus tau and T plus tau.
T plus tau. T plus tau? Well, okay. My transmission. Well, yeah. Okay, if I start transmitting at time t, right, then if some other device starts transmitting within time tau, so let's say this distance is tau. Within time tau of my transmission, if some other device starts transmitting at this time, then our transmissions are going to overlap, right? His transmission is going to kill the end of mine, right? But also, if he started transmitting, I think tau earlier. Is it tau earlier or t earlier? Let's see.
But as long as you don't receive anything, you can receive stuff until T plus tau. Because if the device is transmitting, you'll...
Well, okay, if he transmits after this time, he's in the clear.
Yeah.
His transmission won't overlap with mine.
You receive it. It's not about when you send it or you receive it.
Not when I receive it, when the receiver receives it.
Will you receive at the same time as you receive it?
True, yeah. But if he starts transmitting at this time, oh, wait. T plus tau. So he has to finish transmitting. Wait, all right, now I'm getting totally confused. Well, look, all right.
Yeah, if you finish transmitting before T plus tau, then you're good.
He finishes transmitting before T plus tau. Before this little T plus tau.
Or if you receive the end of his transmission before T plus tau.
Let's see. If he finishes transmitting at the same time as me, if he transmits at the same time as me, our transmissions are going to collide, right? If he starts time t after me, then there's this gap of tau. So he can start transmitting at time t minus tau, I believe. Right? This distance here is tau. Right? If he starts here, then no, I'm sorry. He can start right after me. He can start right there, right? If he starts at this point in time, then his transmission will reach the receiver a time tau later, right after mine finishes, right? So basically, he can start here. So he's not allowed to transmit at any time in here, or our transmissions will collide, right? Yeah.
The tau at the end of the big T?
Tau
Because
is-
if, like you had it earlier, you just erased. Because if the receiving time, if it takes tau time to send, then as long as your message, if the other sender's message is tau before yours, then it'll get through. Because it's like...
All I'm saying is he cannot, when can he not start his transmission? He cannot start his transmission at any point in time in this interval. If he starts anywhere in here, okay, then his transmission will collide with mine. Right? The beginning of his, if he starts anywhere in this point of time, then the beginning of his transmission will collide with some part of my transmission. Right? So let me just write this down and then we can talk about it. If another sender starts transmitting in the interval, okay, and the key is I'm talking about its starting transmission. Starts transmission in the interval t, comma t plus t, our transmissions will collide. At receiver, okay, because his will interrupt mine, because, or its transmission okay? But that's not, maybe what you're getting at is that's not the only problem?
No, I'm thinking like this sender has like a tau, essentially like a tau buffer time. So
Let's say tau, think about it for the case where tau is 0. Where tau is 0, it's easy to see. Or where tau is 0, we can't start, his transmission cannot overlap with mine, right? Or it'll collide. And if we increase tau, it's not going to make a difference in this case. Because no matter what, they're both the tau is delaying both transmissions. So it's both going to, whatever we do is going to happen at the receiver a time tau later. So if the other device starts transmitting in the middle of my transmission, it's going to interrupt my transmission. It's going to happen at the receiver time tau later. The fact that it happens at time tau later doesn't matter. Okay? So if it starts transmitting in the middle of my transmission, it interrupts me. Okay? However, there's also a collision in this interval of time t. Okay? If that device had started transmitting at any point in time in this interval, and I start transmitting here, there's going to be a collision. Okay? If another device starts transmitting in this interval, which is t minus tau t, then my transmission interrupts its transmission. So there's a collision range of 2 tau. Two t, sorry, thank you. Okay? Yeah.
If the sender 2's transmission. Oh, okay, no, okay. I'm good.
Right.
We're assuming
I'm
that,
good.
that according to the protocol, all messages are the same.
All messages are the same length t. All propagation delays tau are the same. Okay? And any interference at all corrupts the message. Yeah, Sebastian.
Definitely. Yes.
Okay? So now, so think of it this way. I'm going to start transmitting at time t. Okay? That means that no other device can transmit during the interval t minus capital T to t plus capital T, right? So my definition is my definition is start at time t. If no other device transmits during the interval t minus capital T, t plus capital. Okay? So to compute this, so this P of, where'd it go? Xi equals 1, given S, let's say I equals T, this is going to be the probability that the device J is not transmitting at time t minus t times the probability, let me just say it this way, not transmitting at that time, and device J's timer does not expire within time t. Right? For all j. So I should say probability for all j. Yeah, David.
It means that it doesn't start transmitting?
No, that's not trans. It doesn't start transmitting.
The end of the
Yeah, that's right.
How does
Yeah.
My question is, my device can't calculate when another device transmits. It can only measure when it receives what it transmits.
Right. Well, your device can't, but we can still do the calculation. Right? Just as observers of the system. So I'm not actually implementing the protocol. I'm just going to compute the probability. Right? Okay, actually we've already gone way over. So we'll pick up from here next time. We'll finish our analysis of Aloha. Next time we're just going to start by computing the formula. And that's next week, next Monday.
Remember, when I started, this is the one, right?